In this video, we're going to start talking about the second derivative test. But before we do that, we need to talk about intervals of concavity. We need to talk about what it means for a function to be concave up on an interval and concave down on an interval. Alright, so the function f is said to be concave up on the interval I if the first derivative is increasing on that interval I. Alright, so here's an example of a function that is concave up. So let's call this f of x. Alright, so now we need to think about f prime of x. Remember that what f prime of x tells us is the slope, and in particular the slope of the tangent line. So if we were to draw some tangent lines through here, and that was not really quite a tangent line. I couldn't see what I was drawing, so I drew it higher than it should have been. But anyway, here the slope is negative, here the slope is approximately 0, and here the slope is positive. So as we go from left to right, the slope is getting bigger, the slope is increasing. Well, that means the derivative is increasing. The function f is said to be concave down on the interval I if f prime of x is decreasing on I. So again, we're going to be looking at the slopes. So if you draw a tangent line here, the slope is positive. Through here, the slope is maybe 0, and then over here, the slope is negative. So again, as we go from left to right, the slope is getting smaller, from positive to 0 to negative. That means that the derivative is getting smaller. The derivative is decreasing. Alright. So, think about what this means. We said that if we have a function that is increasing, that means its derivative is positive. So f prime is an increasing function. If f prime is an increasing function, that means its derivative is positive, which is to say that f double prime of x is positive. And in the event that we have a function that is concave down on an interval, that means f prime is decreasing. Well, remember, if a function is decreasing, that means that its derivative is negative. So f prime's derivative must be negative. In other words, f double prime of x must be negative on that interval. So that brings us to this theorem. Let f be a function whose second derivative exists on the interval from a to b, the open interval from a to b. If the second derivative of x is greater than 0 for all x on that interval, then f is concave up on that interval. If the second derivative of x is less than 0 for all x on that interval, then f is concave down on that interval. This brings us to the second derivative test for extrema. Let f be a function such that f prime of c equals 0, and the second derivative of f exists on an open interval containing c. Alright, so what we've got then is a critical number, but not just any kind of critical number. It has to be a critical number where the derivative is 0, not where the derivative is undefined. You've got to have a horizontal tangent line. If it so happens that the second derivative is positive at c, that means that the function is going to be concave up around c, and so what you've got is a relative minimum. If the second derivative is negative, that means that the function is going to be concave down around c, and we've got a relative minimum. And if the second derivative if the second derivative at c is 0, well, you can't say that you have neither a maximum nor a minimum, because you might. It's just that the second derivative test fails. And what do I mean by fails? It fails to give any information. You could still have a maximum or minimum, it's just that the second derivative test cannot detect it. So let's look at an example. Let f of x be x cubed minus 6x squared minus 15x plus 1. Find all relative extrema using the second derivative test. So what do? First we find all the places where the derivative is 0. The first derivative is 3x squared minus 12x minus 15. And while we're at it, let's find the second derivative. Alright, so we've got the first and second derivatives. Now what we need to do is find all the places where the first derivative is 0. Factoring seems like a good idea to me, so let's take out a common factor of 3. So the first derivative factors into 3 times x minus 5 times x plus 1. There are two critical numbers then, x equals 5 and x equals negative 1. So what the second derivative test tells us to do is to substitute these values into the second derivative and observe the sign. Here's our second derivative. So f double prime of 5 is going to be 30 minus 12. That sounds like it's positive. And then f double prime of negative 1 is negative 6 minus 12. That's negative. So if the second derivative is positive, that means the function is concave up. And so we have a relative minimum at x equals 5. And if the second derivative is negative, that means the function is concave down. And that means we have a relative maximum at x equals negative 1. To find the y coordinates, what we need to do is substitute the x coordinates back into the original function. So let's see, if x equals 5, we're going to get 125 minus 150 is negative 25 minus 75. Let me try that again. 125 minus 150 is negative 25 minus 75 is minus 100 plus 1. Maybe it's negative 99. And at x equals if x equals negative 1, we're going to get negative 1 minus 6 is negative 7 plus 15 would be 8 plus 1 more would be 9. I may have those y coordinates wrong. I'll leave those for you to check. So the second derivative test is fairly straightforward. It's a little bit faster than the first derivative test. You don't have to worry about testing intervals. All you have to do is plunk the numbers down into the second derivative and see what you've got. So it is a little bit quicker at identifying relative extrema, but it's not so reliable as the first derivative test. The second derivative test cannot identify relative extrema that occur at cusps. Remember we said that we had to have a horizontal tangent line, that the first derivative had to be 0. And sometimes it fails to recognize extrema occurring at horizontal tangent lines. Let's do an example. Find all relative extrema of f of x equals x to the fourth. Well, whether we're using the first derivative test or the second derivative test, we start out the same way. We take the first derivative, and that's going to be 4x cubed. Alright, there aren't any, the original function has no discontinuities. The only way that we're going to get a critical number is if this is equal to 0. That tells us that x equals 0 is the only critical number. Well, what happens when we plug in, or what happens when we find the second derivative? That's 12x squared, right? So if we look at the second derivative at 0, we get 0. The second derivative test isn't telling us anything. However, you may know what the first derivative test, or what the original function looks like, x to the fourth. It kind of looks like this. It's a skinny shape, sort of like a parabola. Technically it's not a parabola, but it has that same general feel to it. So the second derivative test cannot find that minimum, but the first derivative test can. How would we use the first derivative test? Well, we would look at our intervals from negative infinity to 0, and from 0 to infinity. Pick a test number, say -1 and +1, and then look at the sign of the first derivative. The first derivative is 4x cubed. That's going to be negative on the left side of 0, and when x equals 1, it's going to be positive. So that means that f of x is decreasing and then increasing, and so we know we have a minimum.